Hey everyone, welcome to the second video for section 3.7. So in this video, in the first video we talked about the mass on a spring and how considering that leads us to a second order linear constant coefficient ODE. So in this case, in this section we're going to start looking at the first case of this sort of setup where we have what are called undamped and free oscillations. So I'll define those terms in a second once we get into it, but that's basically what it said here. It was the first type of a problem you can get out of the mass on a spring system. Let's go ahead and jump on into it. So in this video, we're talking about what are called undamped free vibrations. Now basically these two terms serve to make our equation a little bit simpler to deal with for the first case. So by a free vibration, what I mean is it's unforced, which means our little f of t term is 0. By undamped, what I mean is that my gamma, my damping coefficient, is 0. So if I plug in these two things, my equation becomes really simple. My equation just becomes mu double prime plus ku equals 0. And now this we can look to solve explicitly because what is the characteristic equation of this ODE? It's just mr squared plus k equals 0. R squared equals negative k over m, which means r equals plus or minus I times the square root of k over m. Because remember, k and m are both positive constants, so this ratio is positive, which means we're taking the square root of a negative number, which gives me an I that comes out. So if I give a name, say omega 0, to this square root of k over m, what I get is my general solution when I write it back in terms of sines and cosines is u of t is going to be c1 cosine of omega 0 t plus c2 sine of omega 0 t. And as we see, these solutions don't decay in time, they don't grow in time, they just stay consistently oscillating between proper values because there's no damping. There's no way that for the system to lose energy because it's just at the same energy the entire time. There's no damping, there's no resistance to get rid of that energy, or there's no forcing to add in energy. So now if I look at this formula, it's a sum of trig functions here. But if I can write things a little bit differently to make it look a little more intuitive. So I can write this in the form u of t equals r times the cosine of omega 0 t minus delta. And how does that work? Well, if you look at the formula for difference of cosines, right, this is r times what? Times the cosine of omega 0 t cosine of delta plus sine of omega 0 t sine of delta. So the normal difference formula for cosine. Now if I want to match up these coefficients, the delta and the r, to my c1 and c2 from above, I need that r cosine delta equals c1 and r sine delta equals c2. But this is similar. This is very much like polar coordinate transforms from Calc 3 or Calc 2, wherever you saw these for the first time. The normal r theta polar coordinates that we use in the Cartesian plane. Here we have delta instead of theta, but the idea is the same. So if I want to go the other way, I know that r is going to be the square root of c1 squared plus c2 squared, and then the tangent of delta is going to be c2 over c1. And then when we're solving for L, we have to be sure we pick the right quadrant, but that just looks at the signs, S-I-G-N-S, of the sine and the cosine term to figure out that you get the correct quadrant. So we now want to sort of define all these terms are. So we call this R is the amplitude of our oscillation. This omega 0 is the natural frequency, and this delta is just a phase factor. The delta basically tells us where along the oscillation curve we're starting our experiment. It'll depend on initial conditions and all that stuff pretty explicitly. And as I mentioned before, if you look at the oscillation, it's always of height r. So if you can solve for r, you know exactly how high it's going to oscillate, and it's going to stay there for all time because there's no way for the system to lose any energy. All right, that is the point for this video. In later videos, we're going to go through and see a bunch of pictures of how all this stuff works and take a look at the equations themselves. But now this is the introduction to all these different areas. So I'm going to write up a problem to you guys where I basically want you to find this r, omega naught, and delta for a certain setup. So I'll write that problem up for you right now. Also, I realized I missed something, and I'll hit that real quick right now because I wrote it in the problem. And that last thing is the period. So the period is how long it takes for there to be one oscillation, and the period is just given by a capital T, which is 2 pi over omega 0. So it just converts the frequency into a period like you would for any other kind of oscillation. So there's the problem for you guys to look at. Take a look at that. It shouldn't be too hard to figure out what all these things are for this problem. You can leave the phase factor in a tangent if you want. It's not a big deal. All right, so that's it for this one. Thanks for watching. In the next video, we'll now have gamma be non-zero and deal with damped oscillations and see what kind of stuff we can see from that. Thanks a lot for watching, and I'll see you in that one.